IEB schools or the GDE, they love to apply this in the real world, because this is really what sequences is about, is looking at, you know, marathon runners. Sometimes they love those examples where they have shaded squares and all kinds of things. Check out the supplementary paper or the, you know, the final. They love to bring this in. And I'm going to do a real world application quickly. If you have a look at this, it says a rubber ball falls from a height of 1 meter above the ground. It bounces back to a height of 9/10 of a meter. It then falls again and returns to a height of 9/10 of the immediate previous height. Now, the problem with this, it's very theoretical. Okay, many times in an exam they will give you more realistic, like you check the worksheet, you've got a tree that's growing and it grows to a certain point and never grows beyond. But let's try and analyze this a little bit. Okay, so I'm gonna draw a little picture here. Have a look. If you have a look, let's have a look. Maybe we can enlarge this a little bit so we can see what's happening with the picture. Okay, now have a look at this. The ball is falling from a height of 1 meter. So the ball was over there. It drops down. Okay, it then goes up because it reaches 9/10 of the previous height. Okay, but what goes up must come down. Okay, so it goes up, gravity pulls it down, and it goes obviously the same distance. Now what's going to happen? It's going to now bounce up again, 9/10 of the previous height, 9/10 of that. So what goes up comes down, 9/10 of 9/10. Okay, now let's have a look at this. The next time it goes up, it's going 9/10 of the previous height. And this guy, what do you know about that? Is going to be 9/10 squared. So we're talking about 9/10 of 9/10 squared. And then what goes up comes down, so that's exactly the same now. Okay, and so it's going to continue to bounce and carry on. So what would be the first question that they could ask you? Now this is a little bit tricky, because have a look here. It says there, show that the total distance moved by the ball up to the time it hits the ground for the 5th time is given by this formula. Okay, a bit nasty. Show that the total distance moved by the ball up to the time it hits the ground for the 5th time is given by this. Now, obviously, I suspect that this is a geometric series. Okay, now let's have a look. All right, we're going to go and have a look at this. It's going to hit the ground 1st time, 2nd time, 3rd, 4th, and over here is the 5th time. So let's create a little bit of a series. Have a look at this. The distance is, well, 1 meter first. Let's move that down. Okay, there's the 1 meter. Plus, what do you know? There's this distance. It's gone up and down. So it's 2 of those, which would mean 2 of the 9/10. Now look at the next one. This is going to be, you've got 9/10 squared here, but there's 2 of them. So it's actually, these 2 together give you 2 of the 9/10 squared. Okay, then we've got 2 of 9/10 cubed plus 2 of 9/10 to the 4th, and that'll give us hitting the ground for the 5th time. Okay, you see that there, hitting it for the 5th time. So it gives you the 1 plus you got 1, 2, 3, 4 of those. 1 and 4 of those guys. Okay, now let's follow this through. Definitely, I can see, look, there's a 1, but over here you've got a common factor of 2 and 9/10. So let's take it out. So if you do that, ignore this for a bit. Let's just blot that off for a moment. Let's have a look at that. Okay, if I take out the 2 9/10, you've got the 1 plus 9/10, 9/10 squared, 9/10 cubed. Okay, now what do you know about this thing? Let's move that in there. This is geometric. Okay, a nice little geometric series. The first term is, that's A, 1 minus the constant ratio is 9/10 to the number of terms, 1, 2, 3, 4. Okay, all right, and what do we know? Over 1 minus R. Okay, which is great, because this is really a level 3 question. It's quite challenging. Now, what we need to do now, at this stage, is apply exponent rules, which becomes quite nasty. Now, watch this. Okay, let's bring that into view. So what have we got here? Let's have a look. Well, 1 plus, now 9/10 times 2, where did I get this from? Okay, well, at the bottom, 1 minus 9/10, this works out to be a tenth. Okay, now when you divide, it's the same as going 10 over 1. Okay, very important. Okay, so what do we know? This gives you, well, think about that. 5 goes into 10 twice. 2 times 9 is 18. Don't add those yet. Remember, you got brackets. And look at this. We've got this thing. Now, what does that give us? If you have a look at this, if you distribute this out, 18 times 1 is 18. And then you've got 18 times the bracket, which is 18 times that bracket, which gives you 19 minus 18 to the exponent 4. Quite a nasty application of the exponent laws here. People, classic exam question where you bring in the geometric. The nasty part of this was, of course, they forced you into using the formula. You couldn't just get a decimal. You had to actually go through exponents, and you had to go and work out with the geometric sum formula. Just to make sure that you're clear on this, what you've got is this. You've actually got this at the bottom here, which is a tenth. Okay, so it's 1 divided by a tenth there. Okay, this guy at the bottom is that. Now, 1 divided by a tenth is the same as 1 multiplied by 10 over 1, which is 10 over 1, which gives us this thing there. Okay, and then, of course, the rest is quite easy. Okay, but again, quite a big challenge there. All right. Okay, let's look at the final question in this sequences and series. Quite important. Have a look at the next one. The second question asks, okay, have a look here. If you look at the question, it says, if this action were to continue indefinitely, that's theoretically, because look, in the real world, the ball's going to eventually stop. But in an ideal world, let's suppose the ball could keep on bouncing all the way forever. Okay. Kind of a romantic concept. It bounces forever and ever. But let's see. It says, show that the total distance covered by the ball could never exceed 19 meters. Okay, let's have a look. What are we going to do? Okay, what are we going to do? Here we find the sum to infinity of the series. Okay, well, this goes on theoretically forever. The constant ratio is going to be 9/10. Does that lie between minus 1 and 1? For sure. Okay, we've got the first term. Now, careful, this one tags on. Okay, this is the geometric convergence series. This here becomes A, that guy A over 1 minus R. And guess what? 1 plus, okay, that gives you, if you work 2 goes into 10 5 times, 9 over 5. And if you work that out, let's see, I'm not using a calculator here, so it's 9 over 5 times 10 over 1, which gives you, well, 5 goes into 10 twice, 9 2s are 18, plus 1 is 19. This is the sum to infinity. Now remember what we did is we converged, we approached that sum to infinity, but we're never really going to get beyond. So what does that 19 tell us? Is that the progressive sums of the terms of the series approach 19, and it means it'll be impossible for the distance to ever exceed 19. A very, very interesting little question. And bringing in the sum to infinity, very theoretical. In the real world, the ball will stop. But if we could, there's an ancient Greek that was named Zeno. And he did this. This kind of question is very exciting, because what he looked at the Greek is he said, this Greek guy said, if you theoretically look at this, if you go from 0 to 1, okay, and you halve, you get 0,5. And if you halve that distance, well, you're going to keep halving. And in fact, you'll keep halving infinitely, and you will never ever be able to get to 1. It's kind of like me standing here and there's a door. If I keep halving my distance from me to the door and I move to that halfway mark, I could literally, theoretically speaking, never actually get to, I could approach the entrance of the door but never actually get there. Zeno called this a paradox. In the real world, of course, you can walk out the door, but the fact of halving all the time creates this paradox. And likewise, with the ball bouncing theoretically, we're never really going to stop bouncing. But the total distance will approach 19. Remember, the progressive sums approach 19, but we never go beyond that total distance, which is quite exciting. The sum to infinity of this series. Quite nice. You'll see in the worksheet I've got a plant, a little tree that reaches a height, and then it keeps growing, getting taller and taller, but its height never exceeds a certain part. That can happen in the real world where it exceeds. It doesn't exceed. It never goes beyond the height that it can reach. Well, from my side, guys, I've covered really every possible angle of basic question in sequences and series. Look at these, master these examples. We went quite quickly through this DVD. If you want to go back, pause it, check out the example, master the worksheet, and you will be pretty much, capable of handling literally any question on sequences and series. Okay, and then go to your textbooks, do what your teachers did, and I hope you really learned. I've just tried to capture the essence of this wonderful topic. From my side, we'll see you around for the other juicy topics in maths. Have a good one. Cheers.